This is the Caledonian Canal, and it is the most beautiful canal in Britain. It was built for ships of 400 tons, designed to transform the Highlands economy. It employed hundreds of men for years, and it makes the English canals with their narrowboats seem half-hearted. But it was never successful. It didn't fully realise its potential. One of the few canals to be built with public money, it was started in 1803 by Thomas Telford.
Linking Inverness in the north with Fort William in the south through the Great Glen, it was hoped that instead of sailing around the dangerous north coast of Scotland, the canal would become a safe route for ships for years to come.
The idea was that it would bring trade and industry to the region and kick-start the economy, because the Highlands were going through a massive period of unemployment.
Improved transport links would transform subsistence occupations such as fishing and farming into profitable industries. This would in turn kick-start supporting industries. How could it fail? After all, it had worked 100 miles to the south. The Forth and Clyde Canal linking Glasgow and Edinburgh had transformed the Scottish lowlands. Canal-side industries had prospered, shipyards sprang up on the banks of the Clyde, and coal from the mines around Glasgow was firing the Industrial Revolution. If that worked, why wouldn't it work for the Caledonian?
It was the onset of the Industrial Revolution that caused the canal to be built, but strangely, it was the success of the Industrial Revolution and the far-sightedness, energy and ingenuity of Glasgow shipbuilders that meant it never realised its potential.
When we look into the failure of the Caledonian Canal, we discover the fascinating story of the development of lowland Scotland's shipbuilding industry.
At the beginning of the 19th century, most of world trade was carried by small boats between 400 and 500 tons, made at small shipyards like this.
These boats were powered by sail.
The problem with sail power is that although the power is free, you can't predict it. It once took a convict ship 3 weeks to get out of the Clyde because of adverse winds. So the search was on to find a biddable power supply so that we could tame nature. Steam power was the new motive force in industry, and a group of Glasgow entrepreneurs wanted to put a steam engine in a boat. But how to provide the propulsion? In 1801, William Symington, a Glasgow engineer, came up with this, the Charlotte Dundas.
It was intended as a prototype tugboat for Lord Dundas, the Forth and Clyde Canal Company chairman. It was the first paddle steamer built as a working boat.
It's a strange-looking boat because we're used to seeing paddle wheels either side of the hull or at the rear as in the Mississippi River boats. This is in a central channel. And then you suddenly realise that it actually looks very familiar, because this looks like a water wheel. And this is what you'd do if you were building a water wheel.
But it wasn't that easy to steer. The hunt was on for a better form of propulsion. In 1812, John Robertson of Glasgow built this, the Comet. Paddles either side of the boat gave much more manoeuvrability. This is a replica, but you get the idea. It was built for Henry Bell, a hotel owner who wanted something to run excursions on the Clyde. Paddle steamers on the Clyde became a big attraction.
But not everyone approved. A clergyman wrote of Henry Bell and the Comet, "He, being puffed up in pride of his abilities, did conceive of a boat that goes upon the waters, not by dint of the clean winds of air as ordained by God, but by means of a fire which burned, and a great smoke which issued from the bowels thereof."
While steam power was progressing, the Caledonian Canal was in trouble. Telford said it would take 7 years to build, so by 1816 it was already 6 years overdue and well over budget. There were calls to abandon it. Telford's response? A wildly optimistic finish date, 1819, and to manage this he accepted lower standards to get the job done. Suddenly, the Caledonian didn't seem to be heading for the success everyone predicted, and as steam technology developed, the situation would only get worse. Even paddle technology would get left behind. After all, paddle power wasn't perfect.
They're very manoeuvrable. This one is used by British Waterways for cleaning weeds. Great for going out on the river on a Sunday, but no good for crossing oceans. The paddle wheel has got an optimum depth at which it's efficient. But if you change the payload of the boat, the paddle wheel efficiency is affected. Plus, if you're going across an ocean, you've got to have enough coal to cross it. And as you use it, the boat comes higher and higher out of the water, and the paddle wheel becomes less and less efficient. Also, it didn't take much for the paddle wheels to come out of the water in high seas. So, another form of propulsion was needed. The solution had been around for about 2,000 years. It's this, the Archimedes screw. And for those 2 millennia, it has been purposefully raising water from the Nile for irrigation. Here at Paisley, where this one lifts 80,000 cubic metres of raw sewage a day. It's a beautiful thing. One of the first machines. The way to get hold of it as a concept is to only watch one piece of water, as it were, as it travels up. Delightful. It's still in use today because it's simple and energy efficient, but nobody had thought to apply its particular principles to a boat until a farmer, Francis Pettit Smith, started experimenting on his duck pond with toy boats. And one day, the story goes, the screw broke. So now, instead of having complete revolutions, he had intermittent revolutions. If you look at the end of this here, it looks very familiar. Snapped off, it looks like a propeller.
A propeller is a short screw. And when it moves through the water, it pushes water out behind. So, as we all know Newton's third law, every action has an equal and opposite reaction. If the water moves backward, the boat moves forward. Thank you, Lou. But which was best? Screw or paddle wheel? The Navy decided. 2 identically hulled frigates with identical engines, the Alecto paddle wheel and the Rattler screw, were lashed stern to stern. But at full steam ahead, the Alecto was towed backwards at 4 knots by the Rattler.
Now you could power a ship with a propeller, navigation became much simpler. Suddenly the northern seas of Scotland, the treacherous Pentland Firth, didn't seem quite so dangerous. So when the Caledonian Canal was eventually opened in 1822, rather than pay the pricey tolls, many ships went over the top. Whilst the Caledonian Canal was being developed to kick-start the Highlands economy, Scottish lowland shipbuilding technology had leapt forward. Steam power was replacing wind power. There were also developments in hull design that would sound the death knell for the Caledonian. The way ships had been built for hundreds of years was about to change.
They were made of timber and they were made by hand using tools like this and adze. You'd use the adze to shape your selected timbers that would make the ribs and knees of a boat. And then when you'd got them all assembled into a framework, its skeleton, you'd plank it. Then you make the seams watertight by caulking them. Feeding this oakum in using your mallet, rather inexpertly, like that. Then it goes in deeper, and pitch went on top
making the whole thing impervious to water. The problem with building ships from wood is that it's very, very labour intensive, and timber has got its structural problems. Its strength to weight ratio is not that good. So the bigger you go, the more massive you have to use your timber, and the closer together you have to have your ribs in your boat, so that you've got an optimum length, because if you build any longer than that, it starts to sag along the keel. The stern goes down, so will the bow. So the shipbuilders came up with something new, and they used it on this beautiful ship, the City of Adelaide. She was built in Sunderland in 1863. She's 54 metres long, 10 metres beam, 6 metres deep. She had Cunningham's patent self-reefing topsails and ran a liner service from London to Adelaide until 1886. She was a fast, smart vessel. It looks like a normal wooden-hulled ship until you go inside. It's an iron frame with teak planking. It's a composite hull. They're still not quite sure of themselves, though. These frames are still only the same width apart as you would put a timber frame, about a span. And there are these great cross members here, bracing it. Very, very strong construction, but with a better strength to weight ratio of iron to timber, it's still a lot lighter, and you could build these ships bigger than any timber ships. So suddenly you've got a lot more space, and that space is for payload, and the payload on this ship was people. She carried immigrants to Australia, over 250 passengers, some of them working the voyage. It took 80 days, and she then returned with a cargo: wool, wine, copper, bark, leather, eggs, beans, chips, bananas. And it didn't stop with composite ships. Out of the great traditions of metalworking in the lowlands of Scotland came experiments with iron and later steel-hulled ships, like this little experiment here, 1,500 tons. This ship, the Glenlee, is made of iron and steel. It uses this long longitudinal member, the stringer, goes right the length of the ship. So this means you've got a very thin, very strong construction. That's all that separates you from the ocean. It's just one open cargo space. It's huge, and this is only about a quarter of it. So, with ships like the Adelaide, you had high speed and high value cargo. This is a bulk carrier, a great big sailing ship. Trouble was, great big sailing ships didn't fit down the Caledonian. After all, the locks were only 52 metres by 12 metres, big for a canal, but not big enough. Even worse, steam engines were being fitted into these iron hulls, and it was much easier navigating a steamship along the difficult northern coast of Scotland than using unpredictable wind power.
But it wasn't all plain sailing, or rather full steam ahead. Haha, small nautical joke there. Although ships could now be built bigger and were steam powered, the steam engines were inefficient. That meant you had to carry a lot of coal, and the more coal you carried, the less cargo you had. And if you decided not to carry as much coal, you had to stop more frequently.
This was fine for coastal vessels, but not for ocean-going ships. So if the steamship was going to work, steam engines were going to have to be more efficient.
This is a Vic 32 in fact, victualling inshore craft. The great fleets, like the home fleet at Scapa Flow, needed boats to supply them with eggs and beer, and these are boats that did it.
They were flat-bottomed, so they could be beached, and they were developed from the Clyde Puffer, the workhorse of the Western Isles. Just like the ocean-going liners, the Vics were steam-powered. The engine and boiler room show just how technology had moved on.
First of all, to improve the efficiency of your steam engine, you have to generate more steam. So you have to improve your boiler technology. The first boilers were very crude. They just sat above the fire and boiled water like a kettle. Plus they were also often square or irregularly shaped, and you have to use cow dung and stuff like that to make them watertight. But new riveted iron technology made them much stronger and made them able to withstand greater pressures. Then, in a further development, this is a map of this engine room. It's good, isn't it? Tubes were added in the boiler through which the water passed. This increased the surface area that was heated and so made them more thermodynamically efficient. More steam at higher pressure.
OK, so we've now got all this nice, efficient steam boiler. But we have to make sure that our engine is as efficient. This boiler is working about 110 pounds per square inch. So when the steam has gone into the first cylinder and exerted its force, there's still energy there. So if you leave it in there to expand, it'll cool that first cylinder down, which means that the next bit of high pressure steam is going to have to reheat the cylinder as well as forcing down the piston. So why not put another larger piston next door to it, so the exhausted steam from the first cylinder can work on that at 10 pounds per square inch. Also, you then add a condenser. That means you've got a partial vacuum as well working on the large cylinder, and bingo, you've got a double engine, a compound engine. What that means is, for the same amount of coal burned, you get much more efficiency. So that would be great on land, but at sea, that's brilliant, because you either carry less coal or you stop less often to refuel, and that means you make more money. One of the best things about these engines is you haven't got a gearbox. They drive the crank, which drives the prop shaft, which drives the propeller. So when you want to stop, you stop the engine and go in reverse. You make it go the other way. So you've got the same power forward as reverse. So they stop beautifully. They dig themselves a hole and sit in it.
So now there are efficient steam engines to power vast iron-hulled ships. So why bother transporting goods in a fleet of small ships when you could stick everything in one big one? With increased payloads, freight costs fell and trade rocketed, but not along the Caledonian Canal. Projected annual tolls were £40,000 per year. Actual tolls were nearer 3,000. With a depth of less than 5 metres, the Caledonian Canal was too shallow for these new big ships. But smaller vessels didn't trust it. Telford's cost-saving measures led to lock gates and canal walls collapsing throughout the 1830s. The Caledonian Canal, the Highland dream, had failed, smashed by lowland inventiveness. Shipbuilding carried on apace.
In 1881, William Denny built this ship model experimentation tank. It was one of the first of its kind in the world, and he went to all this expense because of pioneering work by the engineer William Froude, who discovered that models of ships scaled down behaved in exactly the same way as the real ones. They built these big wax models, 3/4 of a ton, that one. First of all, they'd create a clay mould. Heat the wax up there, and it ran in. You'd add a plug there to give it a hollow shape. Then you'd transfer the whole of that over here to be cut exactly to shape. Oh, it's moving. Wow, it's so quiet. It was actually working then. It's designed to cut the wax model exactly to the naval architect's specification, ready for testing. I bring the cursor down to the point in the plan that we've marked here where we finished cutting last time. You'll notice that I am moving down myself.
Which means the cursor stays at eye level.
Right. By operating the foot pedal very lightly, like that, barest pressure, she's moving and cutting.
The great thing about wax is that it's easy to add or take bits away, so different hull shapes could be designed and trialled cost effectively. The purpose? To find a hull shape that moved efficiently through the water.
When the model's finished, it's put in the tank, which is 100 metres long, 7 metres wide, and can hold up to 2.6 metres of water. It's towed along by a towing carriage. The first ones were steam powered, and it's still the most accurate way of measuring water resistance on a hull, and is at the moment operated by a very excellent team from Strathclyde University who will demonstrate this fantastic tank. Thank you, gentlemen. Proper experimental science. When work began on the Caledonian Canal, engineers allowed for ships as long as 45 metres. But only a century later, John Brown's yard on the Clyde started work on the Lusitania, 230 metres in length, with engines powerful enough to serve a town of 100,000 people. Things had moved on. Next episode, I'll be finding out how bigger and more powerful steam engines led to cleaner and healthier cities.